All right, so what we're going to do is we're going to get started. And again, I apologize. I was chatting with Mr. Snook this morning and I could not get him off the phone. So I'm a little bit late. But I want to remind everyone again that all of my assignments, including the expired no-re assignments, can still be finished through June 9th. Remember, if something in no-re expired, you are still able to go in, click on the expired assignment. You can unlock it because you have coins and you can complete it. Just make sure, like I showed it in the example that I loaded to Google Classroom, you can take screenshots of your achievement page and send that to me via email so that I can update your grades accordingly. Any written work, you can make sure that you send me either in classroom or in my email. Just know that if for some reason there seems to be a delay, I clear out the emails first, and then I'll go and find each individual assignment in Google Classroom and work through that. Also, again, I know I put it in Google Classroom. I want to apologize if for some reason you were looking for something to have been graded. With the 4-day of graduation events that I had to be at, it was a very lengthy day in all cases, and I just did not get a chance to do that. So pretty much today, tomorrow, you'll see that there'll be some updated grades. Continue to work, and I appreciate all of your efforts. So with that being said, we are going to, for those of you that do want a little bit of push ahead, because it is going to be something you will find in pre-calc, we're going to start with our radians. So all of these years we've been talking about, when you're in your calculator, make sure that the mode is in degree or it won't work. Now we're actually going to be able to, as you move into pre-calc, look at your answers in radian measure. So answers are equivalents, meaning their values are the same, but again, they look different because they're in a different unit of measurement. Kind of like feet and inches, 12 inches and 1 foot is the same value, it's just a different unit of measurement. So with that, I've got some vocabulary here that we want to first take a look at, because you're going to see in a lot of the questions that you're being asked to do, it talks about standard position. And with standard position, we're going to be talking about angles. So our vertex of our angle, so a lot of this is going to sound like geometry from last year. Our vertex is at the origin. We are going to have one of the rays of our angle is going to be on the positive x-axis, so moving out to the right. That's our initial side. Any other ray that we place anywhere is called the terminal side. So when we look at a couple examples, you will see that this right here is the initial side, because that's sitting on our x-axis, and this is our terminal side because it ends somewhere else. So again, initial side on the positive x-axis. Terminal side is again where it ends. Same thing here, initial side and terminal. So when we're looking at a lot of what we're going to be talking about, we are going to be on our XY coordinate plane. We are going to be talking about angle measures, and we are going to move between, like here I kind of approximated 135, and that was counterclockwise. Anytime we open up an angle, we're actually going to be opening it up counterclockwise. So we have our positive is the 135, but down here you can see that this angle here even though again it's obtuse, we went clockwise. That's a negative degree. So again, counterclockwise gives us the positive. Counterclockwise gives us positive. Clockwise gives us negative. And then again, what kind of looks normal here, our 45-degree angle, is obviously counterclockwise. So I did, pardon me, include all of that here. Counterclockwise gives us the positive degree. Clockwise gives us the negative degree. Your arrowheads tell you which direction. So if you're unsure of which direction that we're going to be going, because again, most of us might look at this and go, oh, that's bigger than 180 degrees. Here's our 240-degree angle. Because of the way the arrowhead points, that's how we know whether it's positive or negative. So there's all these little things that we've got to pay attention to as we're looking at this so that we know exactly what we're supposed to be doing. Again, we need to make sure that we're paying attention to the details. Now down here, I have what happens if we are drawing an angle that isn't our normal geometry type angle, where in geometry at most we talked about 360 degrees. Most of our angles were obtuse, acute, or right. We never really worried about any angles that were greater than 180 degrees unless we were specifically talking about concave, meaning those things that dented in, those concave figures. So what we end up with here is this idea that if we're going to draw an angle that's 480 degrees, it's bigger than 360. So it's actually 360 degrees and then another 120. So what we concentrate on is we draw that angle that's normal, that 120-degree angle. So that's what I started with here, this 120-degree angle. How I show that it's 480 is I start like I was drawing the tick mark, but I show one full revolution. That's 360 degrees. Then I continue to the 120 and put my arrow. So we account for one full revolution here, and then we finish with the rest of the 120 degrees. I can do this with 530 degrees. I can do this with 750 degrees. Again, however many 360-degree rotations, I would continue to spiral to show that I've crossed that x-axis another time, and the spiral would just keep extending for however many 360-degree measurements I have. So, again, standard position starts with the vertex at the origin. We have our initial side, which is always on our positive x-axis. Our terminal side is anywhere else. Counterclockwise is always positive. Clockwise is always negative. And the arrowheads will always tell us which direction, positive or negative, we're going. So then we talk about what you just kind of saw, which is coterminal angles. Coterminal angles are two or more angles in standard position, again meaning that we have that start at our positive x-axis, with the same terminal side, meaning it stops at the same direction. So for instance, if I looked at 410 degrees, that's actually 360 plus 50. So here's our 50-degree angle. And again, if we're talking about positive, we have to open it up. So notice the orange is opening up counterclockwise in this direction, and then we stop at that 50-degree terminal side. That takes care of the positive 410. Negative 310 degrees, if I graphed that, is if I took away 50. So 50 minus 360, we would end up going in the other direction, where we would start and go clockwise, and where we would end again, our arrow would show us that it's in that negative direction, and that's our negative 310. What's the same in both of them is this idea that we have our 50 degrees. So that tells me that 410 and negative 310 are considered coterminal. And what we did in both was we added 360 and we subtracted 360 to get those two coterminal angles. So we want to find two angles, one with a positive measure and one with a negative measure, that's coterminal with, and in this case, we're going to look at 130 degrees. Well, if we follow this pattern of revolutions, meaning we're going to take that 130 and we're going to make a full revolution before we hit it again, that's the adding 360. If we want a negative, we're again going to go in the clockwise direction, but again moving 360 degrees until, or at least moving in the other direction until we hit that coterminal side where they both end. So what you'll see is this pattern. The 130 degrees, we're going to subtract 360, and we end up with negative 230. We're going to take that 130 degrees and we're going to add 360, and we end up with 490 degrees. So the first thing we did was we drew that 130 degree angle. So here's 130 degrees. What also ends at the same coterminal side, so this same coterminal side right here, was that negative 230 where we went clockwise till we went past 180 degrees and then finished here. We also then took care of the other coterminal angle where we did one full revolution of 360 degrees and then again that 130. So here is our coterminal ray, where now we don't only have the 130 degree angle, but we also have the negative 230, we have the positive 490. We could keep going, just add revolutions. So we could add another 360 here, subtract another 360 here, and we'd end up right at the same position. We just would have to spiral again to show that. So then we're going to look at, I just went in the other direction, negative 130. So we drew that negative 130 degree angle down in this third quadrant now. Here's the coterminal ray. And we took that negative 130 and we subtracted 360. So now notice what direction we're going clockwise around this, but now we went one full revolution until we hit that again, and that's that negative 490. We did the same thing in the other direction. We added 360, and now here's that positive 230. So same idea, just again, we're showing our arrows in the different directions to make sure that we're following the correct path. Again, the trick is add and subtract 360 or multiples of 360, and that will give you your coterminal angles. So what's going to happen is I am going to be posting practice problems, and I already put this in Google Classroom. Those practice problems are not required. I will also then post answers to those practice questions so that you're able to see how they're worked out, and I'm going to post the answers, and then if you want to see how they're worked out, that will be the first part of our class on any given day, as we will go over any questions from past assignments that you still need to complete that you're having trouble with. And we will go over any questions on the new material that I'm, again, essentially providing if you choose to get a jump start for next year. All right, so part of what you're going to see is exactly this question right here. Find the coterminal angles. And again, these pictures do help just to kind of keep straight with what you're doing here if you're having a hard time visualizing that. So we're going to, because all of that we just talked about was truly definitions for what's going to come into play now. What we're working on now is that equivalent value, but again, how are we measuring it? So feet and inches having the equivalent value, but definitely look different when you're working with the numbers. Degrees and radians, they're going to mean the same thing. It is a different form of measurement. They're both talking about the rotation. Again, degrees, when we saw 360 degrees, we knew we went all the way around. When we were talking about 90 degrees, we knew we only went a quarter of the way around. When we talked about 180 degrees, that was only halfway around a circle. When we talked about 270 degrees, that was 1.5 times around the circle. So what we're looking at is this idea that they're both talking about this revolution or those rotations around our circle. And they form the initial side to the terminal side. So again, they're forming that rotation or that angle. 1 radian measure of any angle, so theta, we're naming it because we don't have any other value here to talk about, when it's in standard position with a terminal side that intersects an arc. So here's another vocabulary word from geometry. We have to remember that we're dealing with circles. So an arc is part of a circle with the same length as the radius of a circle. So 1 radian is the measure of an angle theta in standard position with a terminal side that intersects the arc with the same length as the radius of a circle. So here is kind of what's happening. We need to go back and think that circumference all the way around is 2 pi r. If we're talking about 1 revolution, so radius being 1, anything times 1 is going to be itself. Well, a number, 2 pi, times 1 is going to be 2 pi. So what this tells me is that if I'm dealing with this 1 unit of measurement, out here, 1 full revolution will be the equivalent of 2 pi radians. So again, instead of 360 degrees, we have the equivalent measurement of 2 pi radians. So all the way around is 2 pi. You can see that here. Kind of like, again, 12 inches is 1 foot. The same idea here. These are equivalent. Well, then if 360 divided by 2 is 180, half of 2 pi would just be pi. So now think about what we just got done saying. We said if we went all the way around, that was 360. A quarter of that was 90. Half of that. So we're going to kind of look at how that works with our radians. Of course, we're going to want a formula to make that easier instead of memorizing everything. So when we convert, if we have degrees and we want to go to radians, we're always going to multiply the number of degrees by pi over 180. So pi radians over 180. And the reason is we're trying to get radians, so we don't want to divide anything away that has radians. We want radians in our measure, so that's why we're staying in our numerator. If we have radians, meaning we have something with pi, and we want to get degrees, we want to get rid of that pi. So we're going to have that in the denominator this time. So we're going to multiply the number of radians by 180 over pi radians, because we're trying to cancel the pi out of our measurement. So they're reciprocals of each other. and in both cases, we're multiplying. In one, we have degrees and we want radians, so the radians stay in the numerator. In the other one, we have radians but want degrees, so we want to cancel out those radians. So we're going to look at just a couple examples that are going to do this. And what we have is this negative 45 degrees. And we want to rewrite degrees to radians, or if we have radians, we want to make it degrees. So I take that 45 degrees, and you'll notice just because I'm over the top with everything, I lined everything up so that it looks like both are fractions. And here's what I did. I know that my answer, because if I multiply across, is going to have pi in the numerator. I immediately picked up my calculator and I plugged in the fraction to let it reduce for me. Now I understand that eventually you will have to do this on your own because the graphing, if you don't have one of these, those graphing calculators won't reduce the way these do. But all I did was take 45 ABC 180, because that's what's happening. 45, negative 45 pi over 180. And I let that do the job for me. Pushed enter. And now I have 1, negative 1 pi over 4. So it's negative pi over 4 radians. Over here, we have that 3 over 2 pi. Notice how it's in the numerator, so we want to cancel it out to get our degrees. And then we have 180 times pi radians. So our pi is going to cancel. And then all I did was 180 times, and I put parentheses, 3 over 2, and I'd let the calculator do the work for me. Now with this case, it's not as difficult. I will tell you, you're going to have some that are going to be, you may have been able to do this mentally, but if you're struggling, I'd rely on that ABC button just for efficiency, because you're going to have some that might be 5/7, that might be 11/13, and you want to make sure that you don't make any errors when you do have something that can help you be more efficient. Now with these, of course, you can do 3 times 180 divided by 2 in your calculator, and it will do the same thing for you. But I just figured I'd show you that when I did these, I just went straight to the calculator to make it go by faster. In the next two, same pattern. We took that 120, put it over 1, multiplied by pi over 180, and got 2/3. Again, this, the 12 over 18, if you reduce by 10 first, mentally you probably have that 2/3. If not, again, 120, ABC 180, and let the calculator reduce it for you. Just don't forget that pi is still multiplied in there. We had that, I know some of us had that issue. We did a lot of great work with, when we did surface area and volume with cylinders and cones and circles, spheres, we were leaving things in terms of pi, and we would forget after doing all the number work to include pi in our answer. And then here's right now the 5/8. Again, we can multiply 180 times 5 after we've canceled the pi, divide by 8, but again, I just did 5 ABC 8 times 180 and had my answer of 112.5 degrees. So if I want to get rid of degrees and put it in radians, pi goes on top, the 180 goes on the bottom. If I want to get rid of pi, I need to make sure it's now in the denominator. So easy way to remember if you're having trouble memorizing which of the fractions to multiply by. The last thing that we're looking at is there are some major ones that when you move into pre-calc, that, and this is 11, and I don't know why my 11 looked so wonky, that as you move into pre-calc, there's going to be some values that you absolutely like. Pretty much everything we've done in math so far that we suggest just have it memorized. It's going to make life a lot easier and a lot faster, and you won't have to shuffle through 17 different cheat sheet note cards to find it. You will find that, again, when we go from 0, oops, looking at my screen and not at my paper, 0, counterclockwise around, we hit 90 and 180, 270, and then if we come back all the way around, you know that a full revolution is 360 degrees. So I do have, for the most part, my degrees on the inside. But as we hit these, when you think about it, go back to geometry, we had our special right triangles, where we did have, in special right triangles, we did have 30, 60, 90, 45, 45, 90. Up here is another 30, 60, 90 when we draw our triangles. So when you're looking at this, if I was just looking at this first quadrant, and we had 0 degrees and here was 90 degrees, and in this first section here, if I'm looking at this, that angle, again in standard position, is down here. This is our 30-degree angle because it showed that up here, kind of like in our protractors, obviously. If I drew my right triangle now, what I'm looking at is I have this special right triangle where I would be able to figure out lengths and actual measurements to know what that coordinate might be if this guy out here has a coordinate of 1, 0. Now remember, that's a degree, and that's a degree. But if I was out only 1 unit, what would that be? So a lot of these measurements are based off of these special right triangles that we've been working with. If I had our 45-degree angle out here, that means this angle here at the central angle would be 45. And if I looked at how that is, I have a 45, 45, 90 situation. And remember, what we're looking at is our radius. If this is out 1, our radius is 1 everywhere we go. So don't confuse the ordered pair with the radius. It just means that as we rotate this radius, the radius is now the terminal side of each of those angles. If I went up here to the other special right triangle where we had 60 degrees, my radius now extends. Again, if it was 1 here and it was a radius of 1 here and a radius of 1 here, I still have a radius of 1 here. And now my 60-degree angle is down here. My 30-degree angle is up there. And my radius again is 1. So as we look around this triangle, we continue to have a radius of 1. And we're talking specifically about these special right triangles, those increments that we've dealt with since geometry. Don't forget that you did see in a previous assignment that when we have our special rights, let's make this 30 and this 60, that we don't forget that we do have that ratio pattern, that formula, that opposite the 30 was 1 of something, opposite the 60 was 1 radical 3, or excuse me, a radical 3. So 1 times a, radical 3 times a, and 2 times a. So we had a 1 to radical 3 to 2 ratio with every one of our 30, 60, 90 right triangles. And when we had 45, 45, 90, that isosceles situation, we knew that 2 of the sides had to be the same, so that's 1 of something in both places. and opposite the 90-degree angle was that common factor radical 2. So with isosceles, it was a 1 to radical 2 situation. So when you look at how these values that we're calculating, all I did was take 30 degrees, multiplied it by pi over 180, and got the radian. I took 45, just like you saw up here, multiplied it by pi over 180, and got this. And as I go through, you'll see a pattern. Notice what the denominators are. The closer to the x-axis, aren't the denominators 6? Same here, closer to the x-axis, the denominators are 6. Smack dab in the middle, those 45-degree angles, the denominators are 4. Same over here, denominators are 4. And then closer to our y-axis, notice how the denominators are 3. Right on the y-axis, notice that our denominator is 2 in both cases. And these guys don't have fractions. Again, patterns. Those are just patterns that will help, especially if we're looking to memorize and not use that every time. What this does is it does help with something I am going to provide to you, which is called a unit circle. The unit circle is this idea, but all the way around. Unit being 1 was our radius. And so that 1 transitions to everywhere the radius transitions. And so that means that not only are you able to figure out the degrees and the radian measure, but you can also figure out what each of these ordered pairs are in every one of their positions around the unit circle. So I am going to upload a PDF of the unit circle to see if we are able to fill in where those positions are around the unit circle. Again, something that you will be using next year with pre-calc. Here are what I will say are the ones that you probably will have to memorize the most, just because they are first quadrant plus the 180 and 360. Even 270 to some extent, that 3 pi over 2 is for whatever reason one I remember quite a bit, but probably the most common. All right, so let's finish with the last thing that your practice questions are going to talk about, and it's actually arc length. Now, we did arc length in honors geometry, and we did work it out using a different formula. That formula was specifically designed for degrees, all right? So when we're using arc length with radians, I don't know why I have radius. I think it was getting late. If you look at some of my writing here soon, it was getting late and I was starting to fall asleep. We want arc length in radians. So here's our formula. Arc length, for some reason, they've designated with an S. It's a lowercase s. It's not even italicized, really. But then it's radius, and that's why. See? Radius and angle. So arc length, radius, and angle measure, but it's specifically in radians. So we have this example where we have a monster truck with wheels, and see, yep, falling asleep, that's an E. Last year, we went to Cedar Point, and the kids got to ride in those monster trucks that they had out back, so that was interesting. And I didn't realize how absolutely gigantic those were. But we have this monster truck, and it has a radius of 33 inches. So again, not the diameter, the radius. It says, how far does the truck travel in feet after just 3/4 of a revolution of that gigantic tire? So we're not going to go all the way around. We're just going to go 3/4 of the way around. So what we have to do is the amount of rotation of the entire circle. So that's 3/4. And if one full revolution was 2 pi, we want to figure out how far this revolution is in radians. So we're going to take that 2 pi, because we don't want 360. Our formula doesn't work with 360. Our formula works with radians. So if a full revolution is 2 pi, we're only going to take 3/4 of that. So when we multiply, notice of is multiplication, you get 3 pi over 2 radians. Okay, and this is that central angle measure in radians. If arc length has this formula, right there, fell asleep, nodded off. But our formula is arc length is radius times the angle measure in radians. We have our radius, which is 33 inches. Our radian measure, 3 pi over 2. And we end up with 49.5 pi inches. If we do multiply pi, it is 155.43 inches, which does convert because it does ask in feet. So we do have to divide by 12, and that is about 13 feet. So again, we made sure that we talked about one full revolution in radians, so we used the 2 pi, not 360. Now, the equivalent measure, just to show you, in geometry, we had arc length was 2 pi r. Notice how 2 pi shows up no matter what. Times, and it was supposed to be our degree over 360. Well, 3/4 of our rotation, it already tells us 3/4. So you could take, well, what's 3/4 of 360? Isn't that 270? Well, 270 over 360 is going to get us right back to that 3/4. So we're right back to 3/4, and you end up with your 2 pi r times 3/4. So do you notice how right here and right here end up being the exact same thing anyway? So we actually had this formula in geometry. We just didn't realize that it ends up being built in with our radian measure already. So it's going to end up giving us the same thing, that 49.5 pi when we plug in our 33 for our radius. And then everything matches side to side. So last example, and again, forgive me, I messed a bunch up because it was about midnight. A circle has a diameter of 9 centimeters. Find the arc length if the central angle is 60 degrees. So now it's not telling us how far we're going. It's not giving it as a description of 3/4, or in this case, 1/6. It's telling us that we have that 60 degree measure. So the first thing I'm going to do is I'm going to take all of this, and I know that with our formula, arc length equals radius times our angle measure in radians. So our radius, if our diameter is 9 centimeters, is going to have to be 4.5. I need to take our angle measure and convert it to radians. So 60 times pi over 180 ends up being, and again, I put it right in the calculator and reduced, I got pi over 3. So 4.5 times pi over 3. I did move it back to 9 over 2. That way I can cross cancel a little bit better. I did the mental math instead of in the calculator. So we end up with 3 times pi over 2. And we have 3 pi over 2. Again, that is in centimeters because we already converted to radians. And if we wanted to multiply pi in, it's that 4.71. Now, just to show you, because again, it's the same measurement, we're just using a different unit of measurement. So instead of degrees, we changed our unit to radians. But we got our answer in the long run using this formula. In geometry, we did do 2 pi r times degree over 360, that fraction of our circle. Well, 2 pi times that 4.5 times our degree 60 over 360. So we end up with 2 pi 9 over 2 times 1/6. The 2's are going to cancel, and we end up with 9 over 6 pi, which gets us right back to that 3 pi over 2. Because our circumference formula is already built in with radians, you can see that our calculations in both, same work, different form of measurement, but we still end up with our same answer of 3 over 2 pi centimeters. So you will find all of this. Again, I will put all of these notes, including my little help with what I showed you with our unit circle. And I'm going to load the PDF for the unit circle. I will load a few practice questions just for you to kind of look at how to do arc length, to look at how to convert, and to look at coterminal angles. I will put all that in Google Classroom. And we will go from there. So thank you all very much, and have a great day.